and this is build distributed applications the well-architected way. My name is Teddy Aryono. I'm a senior specialist solution architect here with AWS, and together with me today is my colleague, Steven Salim. So Steven is part of Cloud Optimization Success, where he's specializing in AWS Well-Architected framework and some other AWS services as well. So what we're going to do today is basically to share with you a few key challenges that we've seen across the board with our customers when they are building distributed applications, and basically how AWS Well-Architected framework can help you with that. So let's dive right in. This is a whiteboarding session, so obviously we'll use our digital whiteboard here. So yeah, first of all, I'm quite sure most of you are well aware of AWS Well-Architected framework. It's been a while. But just as a quick refresher for all of us, AWS Well-Architected framework is essentially a collection of best practices that can help us and guide us in building and designing distributed applications and our workload on AWS. And we have 300 best practices in our repertoire, and we group them into 6 different pillars that we deem important to run our workload on AWS. And they're essentially operational excellence, security, sustainability, cost optimizations, performance efficiency, and also reliability. Now, what we're going to do today is basically to take some of those best practices and use them as our guidance in addressing common challenges of building distributed applications. Now, before we dive into those common challenges, let me level set with you what I mean by distributed applications. Right? So let's say we have an e-commerce application, and we have 4 different core functionalities in our e-commerce application. So we have order, we have warehouse, payment, and also loyalty. In a traditional 3-tier layer architecture, typically we architect and design our architecture this way. So we have our UI layer or presentation layer in here, and then we have the data layer as well in here to help us connect with our persistent storage. And then in the middle here is what we normally call as application layer that hosts our business logic. Now, in this kind of architecture, let's say we want to introduce some changes to our order functionality. So chances are you need to do some changes in this layer, the application layer, and then the UI layer as well, and also the data layer. So when it comes to deployment, we have to deploy them all together as a single unit of file to our Tomcat containers or your application server essentially. And those deployments actually contain everything, including all of the functionalities that we didn't touch before, like warehouse, payment, and loyalty in our case. So this kind of situation poses some inherent risk, and it discourages people to deploy even more, and eventually it slows down our development velocity, right? Sometimes we refer this architecture as monolith as well. Now, on the flip side, or an alternative approach to build our e-commerce application would be in a distributed manner. So we treat each of those features or functionalities as independent application component. For example, order, payment, warehouse, and loyalty. They have that independent deployability feature, or we can deploy the changes independently, basically. So for example, when it comes to changes, we want to change or introduce some changes into our order functionality. The changes are actually localized only to that domain, which is the order. And we can just deploy them independently without affecting the others. And of course, we have to integrate them all together at the end, in this case via network. So this kind of mechanism or architecture encourage people to deploy even more, and then it speeds up our development velocity. So that's that. Now, with all of those benefits that I've alluded before, it comes with a few challenges as well. One of the most prominent challenges that we've seen with the customers across the board is organization bottlenecks. What do I mean by that? Now, if we step back into our monolith architecture, we typically arrange or structure our team as a single unit, just as we did with our application architecture. So we have, of course, we divide them based on the skill sets. So we have our front-end engineers, we have our back-end engineers, and we have our DBAs as well to help us with the data. Although we divide them based on the skill sets, but eventually they will, act and work as a single team, operate a single application usually in here. So this kind of team structure mostly works with this kind of architecture because, for one, it's a single unit of application. We do everything in there, and we have the same technologies across the board, essentially. Now, chances are, when people move into from monolith to microservices, more often than not, they bring the same mental model with them when they move into microservices. So they bring the same team structure and apply them into a new distributed architecture. Now let me show you what will happen if we do that. So let's say now we have a bunch of engineers here, and we assign them into our payment service here. So we assign them to work on this module or payment service. So chances are they need to learn about specific context in payment. They have to learn about specific technologies in payment as well. In some other week, probably next week, we reassign them to work on the order service. So chances are, again, they have to relearn about specific context for order and specific technologies for order as well. Now, if you can see here, this kind of mechanism, force people to do frequent context switching, and we all know that context switching are expensive. That's one. And another thing that I want to highlight is basically there is a mismatch here between your application architecture, team structure, and your operating model. Now, that's the reason why actually one of the key areas in distributed in operational pillar, we emphasize that we have to choose the operating model, the right operating model, to align with our business outcome. Now, what we're gonna do today in here in the team structure is restructure them based on the business domain as well, just as we did with our application architecture. So again, we have order, warehouse, payment, and also loyalty. And each of these domain here actually should be managed by a cross-functional team. So by cross-functional team, I mean, you have your back-end engineers, you have your front-end engineers, you have your, domain experts, you have your product managers, and so on and so forth. And essentially, they act as a single unit. They work on this order domain or warehouse domain or whatever as a product. So they treat that as a product. They have to have that kind of you build it, you run it mentality. So they need to design it, build it, and run it efficiently and make sure everything runs smoothly. Sometimes we also call or refer this cross-functional team as a stream-aligned team. Now, if you're part of the stream-aligned team, you might ask yourself, with all of those restructuring, now I have a lot more responsibilities and I have a lot more, tasks to work on, and that's where the platform team actually comes in to help. And the platform team essentially is the team who create and maintain a platform, an internal platform, to support your development and deployment. They build the internal services and internal toolings to support the stream-aligned team. Another team that's also important is what we normally call as enabling team. So enabling team, as the name suggests, is the team who helps stream-aligned team to acquire skill sets that they need. For example, now in our e-commerce application, we need to improve our security posture. We need to improve our security posture in our e-commerce application. That's where the security expert actually comes in as the enabling team to infuse that security mindset and security mental model into our stream-aligned team, so that our stream-aligned team can bring that security mindset and infuse them into that application development lifecycle. So that's the enabling team. And last but not least, it's what we normally call as a complicated subsystem team. So for example, let's say our e-commerce application is doing really well and we want to introduce a user personalization service into our application. And chances are we need a bunch of data scientists to do that. So it needs a specific skill sets of engineering to deliver that kind of functionality. And that's actually it's the data scientist. And this is what we normally call as a complicated subsystem team to help you with that. The The idea is to kind of outsource this complicated task into a specific team, in this case it's data scientists, to deliver that functionality and expose them as an API to be consumed by the Streamline team. So by doing this, actually, we clarify all of the role and responsibilities that we need to our team members. They know what they need to do. They know their roles and responsibilities. So that's the human side of engineering that we have to deal with when we are doing migration from monolith to microservices, right? Another thing that's also important is the technical side, and one of the most prominent challenges that we've seen across the board is with regard to application integrations. So again, if we step back into our monolith applications, for example, we have a request coming in here for from the internet into our application. So it goes through order, for example. Now, if it's monolith application, we can just do a direct function calls or direct method invocations into our other modules. We can invoke reserve stock from warehouse, or we can invoke take the payment from payment modules, and so on and so forth. So we do it everything synchronously. This kind of communication model makes sense in monolith because it happens. Everything happens inside the same machine. Because everything happens inside the same machine, it happens really fast. It doesn't really hurt the user experience. The user, your end users typically don't need to wait for that long for that particular transaction to finish. And we don't need to deal with a lot of different technologies as well. So that's one. Again, when we bring that back, bring that mental model into our now distributed applications, for example, we receive the same request coming into our order, and then in that order, instead of invoking a module or a function into in the same machine, we have to send a request through the network to invoke the other functionality of the application. In this case, is reserving the stock from warehouse, taking the payment, and also awarding the points. And eventually, we can send the response back to the users. But by that time, as a user, you are annoyed because it takes quite a long time for the whole transaction to finish. And also, in here, it's actually idle. So the order needs to wait in idle while the other modules or the other service doing their job. This creates two unintended consequences for us. It results in a poor user experience, of course. It's quite slow because everything happens over the network, not a single machine. And it has this temporal coupling. So what I mean by the temporal coupling is even though we design our architecture to be operating in a distributed manner, because of the way we tailor the communication and integration of each application components, they have to act as a single unit during that particular transaction. So they are temporarily coupled together during that whole transaction, right? And it actually deteriorates your SLA. So for example, if you have 99.99% for the whole services that you have, your combined SLA, you can just multiply them together. The combined SLA is actually 99.96%. You can just multiply them together. So a different approach to this is by implementing a loosely coupled dependencies. Now, let me introduce you to Amazon Event Bridge, where it acts as an event bus, intermediary service, to decouple our services, right? So now we have a request coming into our order, same scenario, but now instead of just invoking or sending a request into warehouse or payment or loyalty, we can just put an event. Now, it's called order place, for example. So it has order ID and the detail of the order into Amazon Event Bridge. And Amazon Event Bridge will eventually send and route the event into these three modules, or these three services: the warehouse, the payment, and also loyalty, right? And when we are doing that, we can just sending a response back to our users. Hey, your transaction is now being processed. You can just sit back and relax and wait for the updates. And back to the scenario now. Warehouse will do the reserving the stock, taking the payment for payment, and awarding the points for loyalty, and they will send the events back into Amazon Event Bridge. So in this case, it's stock reserve, payment taken, and points awarded. And Amazon Event Bridge will send the event back into the order so that the order can update the transaction status. So now at the end, we can notify the users that, hey, your transaction is finished and executed successfully. So this improvement we improve the user experience for one. We deliver that perceived feeling that our application is responsive and fast. And another one is we remove the temporal coupling by, introducing that intermediary service to decouple our services. So this is our service, and we decouple them by introducing intermediary service, right? So that's the development side of building distributed applications. Now for the rest of the session, Steven will guide you on the operational side of distributed applications.
All right. Well, thank you very much, Teddy. Hello, everyone. So as Teddy mentioned, in the next few minutes ahead, I'll talk to you about the operational side of distributed application, specifically around how you need to manage the number of resources that builds the application itself. Now, this is particularly important because if you think about how you're essentially decoupling each of the business functions in your distributed application, and you want to achieve independent deployability for it, then what you need to do is essentially run each of them on its own infrastructure. And naturally, because of that, if you think about it, you'll be having to manage more resources, infrastructure resources, I mean. And on top of that, if you zoom in and dive in deeper into looking at, and if you look at how each of the business functions essentially are constructed, if you build it on AWS, essentially what you'll find is that it's actually built on top of one or two AWS services that are bundled together. And for example, let's say we take a look at the warehouse business functions of the e-commerce application that we talked about before. What you find is that maybe it's using an API gateway as an entry point for the service, and then it could be leveraging something like AWS step functions to orchestrate the business activities workflow. Something like maybe storing inventory items or sending invocations message into EventBridge, for example. Regardless of the shape of the architecture, however, when you're working with a bundle of resources like this, there's essentially three things that you need to consider. And the first one is going to be how you're going to manage the configuration for each of these resources. Because for your architecture to work, when you deploy these resources, you need to specify parameters like runtime environment, or perhaps the code location for Lambda functions, and all of these parameters will build out as part of your architecture definition. And the next thing that you need to consider is how are you going to manage the dependency between them, because your application is essentially going to rely on the interconnectivity of these resources. For example, let's say this Lambda function no longer connects to the DynamoDB. Then obviously in this scenario, your application can't store inventory items, right? So the last thing that you need to consider, which is probably the most important of all, is how you're going to manage the change operation aspect of these things. Because when you're working with distributed application, chances are you're not going to be working with just one or two services. You'll be working with hundreds or even thousands of them. And therefore, making sure that you're well equipped with the right change management practice and also tooling will set you up to be able to handle that change operations at scale. So which is precisely why in well-architected operational excellence, one of the best practice that we emphasize is to make sure that you're equipping your workload with the right change management system to make sure that you can handle the operation at scale. And when you're working with AWS infrastructure, one service that you could look at to do that is AWS CDK. So if you haven't worked with CDK before, it is essentially a tool that allows you to build your cloud infrastructure definition using your common programming language, like Python, C#, or JavaScript, and many others as well. And what you could do when you use CDK is basically deploy that inside your environment variable, and leveraging the framework, you can define your cloud infrastructure using your programming language of choice. Like over here, I've actually got an example of how you could actually define some part of the warehouse application that we talked about before in a Python code. And if you see here, what I've actually done is I've defined two separate resources, one DynamoDB and one Lambda function that essentially represent these two architecture, this part of the architecture that we have here. And to define the resource configuration, we've actually specified that as part of the parameters when we define these resources. And to define the relationship between these two resources, what I've actually done is I've assigned the DynamoDB table construct inside a Python variable, and then I've referenced that Python variable as part of the environment variable in the properties of that Lambda function. So this is essentially how we've created an infrastructure definition and managed the dependency. Now, once we've done this, the next thing that we want to do is deploy them in our environment, right? And for this, what you could do is you run a command called CDK deploy, and this is actually part of the CDK toolkit. And once you've done that, what essentially CDK will do, it will translate the code that you have defined here into what we call a CloudFormation template. And CloudFormation will use that to deploy inside your environment. And from that point, CloudFormation will act as the change management agent for resources deployment. To give you an example of what I mean there, let's say this is the first time that you've deployed these 2 resources here. And if you see, for the Lambda function to actually be deployed properly, it actually requires to reference the DynamoDB table name. In this case, what will happen, what CloudFormation will do is that without you having to do anything, it will deploy the DynamoDB first. Once the state of that DynamoDB is ready and the name is ready to be referenced, only then it will call out the Lambda function to be created and then to reference it. So this is essentially how the change operations happen in terms of the dependency relationship. Now on top of that, CloudFormation actually also handle this from a risk management perspective. For example, let's say we've triggered a replacement of a resource. Let's say we've done a replacement of that Lambda function that we have here. Now what CloudFormation will do here is that it will call out the new creation of Lambda function first. It will create the new Lambda function first, and then transfer over the relationship with other resources. And once all of that is done and complete, only then it will delete the old resource that you no longer need. And this is done in such a way because it needs to create a rollback mechanism. So for something happens during those deployment, you can roll back and still have those Lambda functions over here, right? So this is just a quick summary and overview how you can essentially leverage CDK and CloudFormation that works together to essentially work to handle the change operations at scale for your many distributed application resources. The next thing I'd like to talk about in terms of operations is around cost management. So obviously costs are very important to us, and this is precisely why in AWS Well-Architected cost optimization pillar, we also cover one of the best practice to make sure that you're assigning organizational context to your resources. Because using those organizational contexts, only then you can understand the justification of this investment to those resources, right? And the way to do that is you need to apply tags. And the best timing for you to apply tagging into your resource is actually to do that at the definition time, infrastructure definition time, rather than later, because once you deploy it, obviously, it already incurs cost for you, right? And the way to do that in CDK, there's actually multiple ways on how you can assign them, but the most efficient way to do it is to actually apply that at the stack level. And how you do that is you would actually call out a built-in function in the code called tags, and then as part of the function call, you would assign the stack construct that you would define that includes the rest of the resources, and you would pass that on as part of the function call, along of course with the key and also value pair that builds out the tag itself. And what happened here is that once CDK is deployed, it will deploy the CloudFormation stack along with the tags that you've assigned. So the CloudFormation stack will have a tag that you've defined here, and because you've assigned that tags at the stack level, inherently, all of the resources that is part of that stack, Lambda function, DynamoDB, or whatever it is, will inherit automatically get assigned to that tag. So this is one way that you could efficiently assign multiple resources with the tags in one go. Now, apart from that, there's some cases that you might want to deploy tags on individual resources. Let's say you have some resource that you share between tags, right? Now for this one, to help you in assigning these tags and make it easier for you to define them, CDK being built on top of your common programming language, you can actually leverage something like a for loop that is part of your usual Python code, right? And you can iterate through each of those resources and assign those tags efficiently. So, yeah, so that again pretty much what I would like to share with you in terms of tagging. So with that, we've actually reached the end of our presentation. This is what we have to share. But before we wrap this up, I'd just like to summarize the 4 key things that we think you should consider when you are building your distributed application. So the first one is really organizational structure. And essentially what we mean here, because when you are decoupling your architecture into multiple different business units, you need to make sure that you're applying the right operating model and also the team structure that doesn't create a bottleneck on what you're trying to achieve with this distributed model. And the next thing is, when you're working in a distributed architecture, the nature is that your means of communication is going to leverage network. So with this, you want to make sure that you're architecting your way of communication in a way that it doesn't compromise the user experience using the event-driven architecture that Teddy mentioned before, and make sure that it handles from a reliability aspect as well. And the last 2 things, which are essentially the number of resources that you have to work with from operational perspective, you want to make sure that you're assigning yourself and equipping your organizational practice with the right change management, tooling, capabilities, and also practice that can handle the operations of these resources at scale, and also apply organizational context for each of them so you can understand the justification for your investment. So over here, we've also included some QR code that will take you directly into the Well-Architected Best Practices white paper. It will give you a deeper guidance on how you can actually shape your distributed architecture in an optimal way using AWS Well-Architected Best Practices. So if you want to learn more on how you can build AWS using a couple of our services, you can check out the skillbuilder.aws website, which contains multiple labs and as well as, I think, there's also a role-based game as well that can also help you with your training and certification. And yeah, so with that, thank you very much for attending our session. Hopefully this has been helpful. Myself and Teddy will be over there to answer any questions if you have any. And yeah, don't forget to let us know how you feel about this session by filling in the survey. Thank you very much. Thank you.
Thank you, Stephen. Thank you.